turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists. This is the show where we bring you the latest breakthroughs in science, technology and medicine with me, Chris Smith. And now it's time for Titans of Science, where we hear from some of the biggest names in the business. Today, it's the turn of the British Formula One engineer, Dan Fallows. He's currently technical director at Aston Martin, and I went to meet him at their base to find out how they make an F1 car do what it does.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
So I'm Dan Fallows. I'm the technical director here at Aston Martin Aramco Formula One team, and we're here in our fabulous technology campus here in Silverstone.
This is a brand new building.
It is. We've moved into this building nearly a year ago now, and it's part of three buildings that we're moving into. We've moved into the first one, and now we've got two more that are being built, and we're going to move in towards the end of the year.
It's big. How many people work here?
So there's over 800 people work in this building. It's grown quite a lot as a team in the last 2 years. But yes, over 800 people here, ranging from engineering to manufacturing and everything in between.
We're standing in the atrium. The question that is foremost in my mind as I came through the revolving door is, there is an F1 car in the atrium. How on earth did it get in here? Did you take the wall down?
Fortunately, we have enough room to be able to squeeze it in at the back of the atrium. But yes, it does look, when it's in here, it does look a little bit like it's arrived out of space or something.
It certainly looks space age. I've never been this close to an F1 car. Can you give us some of the sort of specs for geeks like me as to what's in front of us, what this is capable of, and what goes into making that thing do what it does?
Well, this is, I think, the fastest racing car in the world. I mean, Formula One cars are in terms of how fast they're able to go around a circuit. The car that we see in front of us is a modern specification up to the latest regulations, and it's around the same kind of size as a family car. It's 2 meters wide. It's just over 4 meters long. It's a little bit longer than the normal family car, but it weighs a lot less. You know, it's around 800 kilograms, which is probably around half the weight of a normal family car. It has a very small engine inside it. It has a power unit, which is a hybrid power unit, which means that it has a normal petrol engine, but it also has a battery attached to that as well. And that produces up to around 1,000 horsepower. So again, you know, probably 4 or 5 times the power that a normal family car would produce. And obviously lightweight with a lot of power means that it does go incredibly quickly.
I was just thinking, I've got a quad bike that I rebuilt. It's 50 horsepower and weighs about the same as that.
Yes, and I can imagine that probably feels fairly scary to drive as well. I mean, it's unimaginable how much what it would be like to drive one of these things. In fact, a lot of times people ask you, well, how fast can it go? But in truth, you know, the top speed is around 200 miles an hour, which by any standards is very quick, but we don't make it go as fast as it could do in a straight line because we're most interested in minimizing lap time around circuits, and so going fast around corners as well as just going fast in a straight line.
There are presumably a range of different elements that go into going very fast and going very fast safely. They presumably are the engine that gives you the push, the wheels that get that force onto the road and hold the road, but then also this amazing sleek design that means that you're not giving half that energy to the air you're pushing out of the way as you go around the track. I mean, is that a reasonable, to my uneducated, non-Formula One way of thinking, is that a reasonable summary? Yes,
it is, absolutely. We have things that make the difference in terms of the performance of the car. The driver is obviously one part of that. But in terms of the design, the way that we build the car, the most important things to us are the power unit, you know, how much energy we can put into the car and the road, the tyres that stick the car to the road, and then the aerodynamics, which is the shape of the car and how we're using the wind at speed to help those tyres perform. And as you say, to make sure that the car is slippery enough to go through the air fast enough.
And is that what you do here in this building? Do you build all these parts, literally hand making each of the parts that are going on there week after week?
Yes, we absolutely do. I mean, it's effectively every car is a prototype. When you make a normal car or normally any engineering thing, you would normally build a prototype and then you build the actual thing. Well, what we build here are prototypes. So it means that we have to be able to do that as quickly as possible and as efficiently as we can. And that means everything has to be made on site. We do make some things externally, but generally everything is made here at the factory in Silverstone.
Where should we start?
I think we should start with the composites manufacturing. You know, that's really the backbone of the car. So I'll take you there and show you around.
Through these doors?
Yes, through here. So the first and most important thing is the absolute backbone of the car, which is the chassis. So that's where the driver sits in there. It's incredibly tight. It's a very claustrophobic place to sit. He sits with his feet up around the level of his chest, so it's almost like lying in bed, so that we have as much available area for us to do all of our clever management of the airflow around the car. And we also even mold the seat to the driver himself. You know, it's a very thin layer of, again, carbon fiber that sits underneath the driver. We need to make sure that that's molded specifically to his dimensions so that he sits as comfortably and as tightly in the car as humanly possible.
Carbon fibre is a relatively new material. What did we use before we had that?
So originally, cars were made with aluminium and metal, a bit like road cars have been for a long time. The problem is that as we're trying to make cars lighter and more complicated, and particularly to be able to make very complicated shapes, but in a way that's still very structurally strong and stiff and safe, then carbon fibre is an absolutely ideal material to use.
To get that winning combination of something that is strong, doesn't have a lot of material in it, so it's really light. How do you design that? What's the trick to that?
We do a lot of development work to make sure that we are making the car as strong as it needs to be, but obviously as light as it needs to be. And you can imagine there's a kind of tension between those two things. You know, we want to make sure that we're not overweight, because any extra kilogram you have on the car is going to slow it down. But we also need to make sure the driver is safe, and also that when the car is going around the circuit, things don't move around more than they should do. So we accept that things are going to move around at speed because air is incredibly strong and there's a lot of force on the car, but we want to make sure we minimize that effect.
Can you embed sensors in the carbon fibre in order to see where the stress points are, how it's being loaded, how it's performing, so that you can gather data on the track, as it were?
Yeah, it's one of the great advantages of carbon fibre. You can embed things in it, and particularly sensors. There are key parts of the car, like the suspension, which is the sort of little stick-like arms that hold the wheels on. It's incredibly important to us that we understand what the loads are that are going through those members, because we need to know, firstly, that they don't go over the loads that we believe that they may break at. So we need to make sure that the car is always safe at all times. But it's also very useful for us to know what those loads are on the car. But there are hundreds of sensors on the car that we're reading as we go around the lap. Some of those are telling us about load. Some of them are telling about pressure. So literally the pressure of the air as it goes around the car, which informs us about how much downforce or how much force there is pushing the car onto the ground. And we can measure all of that as the car is going around.
When I was at Rolls-Royce in Derby, looking at jet engines, they told me that they take the pieces off of their engines in order to see how working life is affecting them, in order to understand how the materials age and so on. If you're building these cars bespoke for each race, do you almost do a post-mortem on the car materials after each race? Do you pull them apart, have a look at how the race has affected them and so on?
We do that every single race, yes. We take the cars completely apart. They don't stay together. They go into their component parts and either get shipped to the next race, or they do exactly what you're talking about, and we strip them down and ensure that the parts that we have run in the race are still fit for purpose. We also do a lot of research work here at the factory to make sure that parts that are going to be able to last the number of races we think.
So how much of the car is actually carbon fibre and how much is good old-fashioned steel or aluminium, heavy-duty stuff that can take a bit more punishment?
I think as a percentage, I would say probably 90% of the car is carbon fibre. The other parts are things like brackets. There's obviously the steering wheel and the steering column, those parts of the steering column that connects the steering wheel to the wheels. A lot of that is metallic. But in reality, anything we can make from carbon fibre, we tend to do.
In order to inform what the shapes of that carbon fibre should be, to get those aerodynamics, so you're not basically wasting energy moving air around. And I suppose the other important function is that it gives you important force downwards onto the road for road holding, doesn't it? How do you arrive at those shapes?
Well, we have a team of people that work in the aerodynamics field. So we do a lot of testing in what we have a wind tunnel, which we're building here on site. We do a lot of testing in a wind tunnel. We also do a lot of testing inside the computer. We can actually simulate a car going around the circuit and how the air goes over the car inside a computer simulation. We do a lot of work on that. And really the aim of all of that is to try to balance making the car go as fast as possible in a straight line with really doing what the tyres are asking us to do. And what the tyres want, and it's true on any car, is that in order to go around a corner faster, they need more vertical load, so they need more pushing down on them. So effectively, the harder you can push down on the tyre, the more grip it will have, so the more ability it will have to get you to go around the corner faster.
Is there not a sort of tension there? Because you want to slow down a bit to go around a corner, but to get that downforce, you need lots of air pushing the car down over the various fins and structures you've created. So is there an optimum speed to go into a corner then? A, to do it fast, but B, to have more control?
Yes, there is, and the person who's the arbiter of all of that is the driver, really. He's the one who will tell us whether we've done a good enough job with the car going into a certain corner. You know, there are things that we can do with the car to make sure that it's optimized for certain corners more than others. Every circuit we go to has a slightly different layout, which means that your priorities are maybe slightly different. And we can set the car up differently for those circuits. So for somewhere like Monaco, you basically put as much downforce as you can on the car. And in places like Monza in Italy, it's a lot about straight line speed, so you take all the downforce off the car, really. So we have to try and think about those even while we're designing the car, but also race to race.
So we've done what it looks like, how it holds the road from an airflow point of view. Where should we talk about next, and where's next on our trip?
So I think the next thing to look at is, as we go slightly further down the corridor, is into where we're actually manufacturing the car. We have a large facility here at Silverstone where we're manufacturing the metallic parts of the car, the brackets and all the other things we talked about. But I think if you can bear the background noise, then I think it's really worth having a look at.
Let's go and take a look. You were right about the noise.
Yes, it is quite noisy in here, and actually it gets even noisier than this. What we have in here, as you can see, it's a very tall room, and it needs to be this tall because some of the machines that we have here are very tall themselves, and they have components that sort of move up and down. But in reality, they're just very posh versions of what some people even have in their garage. So lathes and mills, which are just machines that have like almost a sort of drill bit at the end of them, and they're able to cut into various materials. So we use things like we call tooling block, which is it's almost a kind of wood type of substance. And then we have at the other end of it, we have traditional metals like aluminium and steel, and these machines are designed to very, very accurately cut into those materials and produce shapes that you want. Now you will either use the final component directly on the car itself, or they will be making molds that we can then apply carbon fibre to, and so that will be the final component.
They look space age. It's almost like the TARDIS in Doctor Who, all of these pods that have pipes and wires and things, but there are no people. Is this all basically computer driven? Someone sitting at a computer telling these machines what to do?
Yes, and it's something that's really taken off over the last sort of 10 or 20 years, that everything we design on a computer in what we call a CAD system, and we then can in the same system say how we would like that to be made. So it's not just about designing the part, but also saying, I'd like this to be made in a certain way. And now that's all done upstairs. We can literally pipe that down electronically to these machines. Somebody can come in, put the correct material in the machine, and then the machine can then go off and do exactly the shape that you want. So the whole process is almost entirely automated.
And someone could say, I think we want to adjust the shape of the front of the car just by a fraction of a millimetre because of some data we got from a race last week, and you could have a new front end knocked out by the end of the day.
Yeah, I mean, it's like you've been here. That's exactly what we do. We do this Skoda kind of thing all the time, and it sometimes is fractions of a millimetre. But we see that we have something happening on the car that we're not happy with. So with all our sensors, we can tell a lot about the car as it's running around. And if we decide at the end of a race weekend that we want to do something differently, we can have that designed. We can have it thought about, designed, and manufactured within a week and on the car for the following weekend. So it is that quick.
It's also very loud. Should we go?
Yes, let's go to the next bit.
That's a relief, but it's an amazing production line that you've got basically the researchers with the data modelling something, turning it into something that then becomes reality, all within minutes.
It is very quick, and the other part that we don't see in this area but is in a different building, we also have what we call additive manufacturing facilities, which is
3D printing.
3D printing, exactly. Yes, so they are they're literally like 3D printers that some people even have at home now, and there's a lot of them in schools, and they are basically large versions of those. We can use lots of different ceramic materials in those, and some parts of the car are now being built in those facilities as well. The point about that is it's even faster and even more complicated shapes that you can build without having to resort to these very noisy machines in there.
So we've seen how you basically make the things that then become the visible outer, but also some of the other bits of the car. We've talked about the fact that going very fast involves good air profile and so on, and how that gives you also force down to keep the tyres on the road. What do we need to talk about next?
Well, I think the next part we can see as we walk down here is the area that we actually put the cars together. It's a very important area for us because obviously there's a huge amount of work goes into all the different components, but the most important thing is it all comes together in a coherent car. And that's a surprisingly big challenge. And once we get to the point where we do have a car, we then need to start thinking about how we're going to operate that at the racetrack. So one of the things we do here, in what we call our race bays, is we put the cars together, and we also have an area where we can practice our pit stops, and the mechanics can practice putting the car together as fast as possible. One of the things that you can imagine does occasionally happen at the circuit is that we have an accident, we have a crash. Sometimes if you ever watch Formula One, you see that there's sort of parts flying off the car, which all looks very alarming. But one of the things that we do when we're designing a car is to make sure that in the event of a crash, the energy that's involved in that crash is dissipated into those parts. So when you see parts flying all over the place, that's usually a good thing for the driver because that energy is being used into flinging those parts around the circuit rather than actually going into the driver themselves.
A bit like crumple zones, which we engineer into cars to absorb the energy and slow down the rate at which it's transmitted from the thing you've driven into to you.
It's exactly that, and we have some of the technology that's been developed into Formula One is now in road cars in that respect. So we can see a car here again, and there are some large areas of the car which are actually dedicated to exactly those crumple zones. There's a part of the front of the car we call the nose, which holds on the front wing, the very large aerodynamic device at the front, and that in reality is just one large crumple zone. And we have two of those zones on the side of the car, and then another one at the rear. And if you look at the very top of the car, on the part just behind the driver that looks like a snorkel, that has a number of functions. It's an air intake for the engine itself for some cooling, and also it is actually a roll structure. So it is a very stiff structure. So in the event that the car flips over and lands on that, it will not break and it will protect the driver. You could put two double-decker buses on the top of that and it would still not crumple. So it's incredibly important that those things are able to withstand high stresses and also the energies of a crash.
Are those the sorts of forces that, at the sorts of speeds they're doing, they're going to be experiencing then?
They really are. I mean, from when we talk about the downforce on the car, we measure it really at top speed in tons.
Really? So if that could drive upside down, say it could operate upside down, at full speed you could probably drive that upside down and it would have enough force holding it onto the ceiling?
It would be nowhere near top speed. I think the last time I looked at it, I think it was about 80 miles an hour that it could drive upside down, drive on the ceiling. So, by the time you're doing 100 miles an hour, it would easily be able to stick itself on the ceiling.
I sort of thought that might be the case. I'm still amazed.
It's extraordinary, and I think sometimes when you're designing the car, you sort of forget about the forces and just what we're asking this car to do. I mean, just the amount of work that the tyres are doing, the amount of energy that's involved in the whole thing is absolutely staggering.
How much of this can you actually change trackside during a race?
Well, clearly, the longer time you spend not going anywhere, then the worse that is for your overall race performance. So we try to make sure that we spend as little time stationary or in a pit stop as we possibly can. But the things you can change once you're in a race are quite a few. But the majority of the time, we would just change the tyres. We can change those in just over 2 seconds, which is quite an extraordinary thing to see.
A whole lot?
Yeah, all 4 tyres and wheels, we can change those in around 2 seconds. But if necessary, for example, if we have some damage on the front of the car, we can change the front wing again in a matter of seconds. And also, even if the driver has a comment about the way the car is behaving, we can make some small changes to the car, particularly on the front wing, if we need to. But in general, when you see cars come into a pit stop, it's generally just to change the tyres and then go out as quickly as you possibly can.
Are you in conversation with the driver during a race, or is it a one-way flow of information? You're feeding them tips and things?
We are in constant conversation with the driver. The driver has a race engineer who's the single point of contact, one person they can talk to, and they're telling them about how the car is behaving, what they might want to do at the next pit stop if they did want anything changed. But I think more importantly, the race engineer can tell the driver a lot as well. They can give them some situational awareness of what's happening in the race. Managing the tyres and the way they behave is a critically important thing for us, and we have an enormous amount of data that comes off the car that tells us a lot about what we might need to do, how we might like the driver to be driving the car, and communicating that to them is obviously a very important job.
That's real-time flowing in off the car to you trackside, so you can see all the different operating parameters.
Literally hundreds of parameters that we can see. We have a number of engineers at the circuit that travel around with the race team and the car, and they'll be looking constantly at the data as the car is going around on track. We also have another area which you can see just up the stairs from here, which is called mission control, a little bit like on space programs, where we have another around 30 engineers who are looking at the data, again, live from the circuit. And everybody will be looking at something slightly different just to make sure that all the systems on the car are working exactly as we want them to.
Can we talk about the tyres for a minute? I changed the tyres on my family car recently. It cost me an arm and a leg. How much would one of those cost, and how much does each one weigh? We
have a deal with our tyre supplier Pirelli, so they supply all the tyres for the race. So fortunately, we don't have to buy them individually. We have an arrangement with them over the whole year. But I dread to think how much one of those would cost. We use, over the course of a race weekend, we use normally 2 to 3 sets of tyres on each car in the race. And then we have several other sets that we use during the race weekend. So it'll normally be another 2 or 3 sets that we use in each of the practice sessions, and then another 3 sets in qualifying. So, you can imagine 10 to 12 sets of tyres that we have available for the whole race weekend. And that's not including in case the weather changes and we need to start using the wet tyres. We also have sets of wet tyres that we can use as well.
The demands placed on them is considerable. Their job is to get the force onto the road, propelling the vehicle along, translating the energy that's coming out of your engine. What are the specifications you're looking for in tyres like that? Do you need a certain kind of rubber that changes its temperature and operates very warm? I mean, how do you get them to perform right, and what are the right conditions?
The structure of the tyre itself is designed to make sure that the contact patch, so the part of the tyre that's touching the road, is as big as possible, at any given time. And that's important because the bigger that contact patch you have, the more adhesion you have, and the more ability you have to generate grip with that tyre. So that's why we have, compared to a normal road tyre, the size of what we call the sidewall, so the height of the tyre relative to the wheel itself is quite tall. That's all about making sure that as the tyre is being pulled sideways by the car, that it still remains in contact with the road as much as possible. And then the rubber on the outside of it is a very carefully designed compound which is sensitive to temperature, so we need to make sure that we keep it within a certain operating range. But when you get it to the right temperature, which is around sort of 80 to 90 degrees centigrade, the rubber becomes incredibly sticky. And when you get it into that range, that combination of the downforce on the car and that very sticky rubber means that the grip and the lateral acceleration you are able to generate on the car is absolutely enormous.
Upstream of those tyres is, of course, a gearbox and an engine.
Yeah, so the engine is a very important part of the the puzzle for us. We have a certain amount of fuel that we're allowed to use, just over 100 kilos of fuel that we can keep in the car. And that represents, an amount of energy that we have to spend.
And what is that fuel? Is that kind of unleaded like I buy on the forecourt, or is it some special blend?
It is a special blend, but in truth, it's more similar to road car petrol than you'd think. It is an unleaded fuel in the same way that you would be able to buy in a normal forecourt. But it has, yes, some particular additives to it to make it particularly suitable for these engines.
So can you tweak what you put in that fuel?
There is a certain amount of variability. Different teams have access to different fuels which have different compositions, but in general, they're very similar.
You have 100 kilos of fuel. You have to make that last a race. How does that get factored into how you make the car perform?
Yeah, so there's always a trade-off between the amount of power that your engine can generate and how efficiently you can use that fuel. The other thing is that it is a hybrid engine. We have what we call an energy store, but it's basically a posh name for a battery that is able to be charged and deployed at certain times during the circuit. And we get a power output of 120 kilowatts out of that battery, so it's a large amount of power that we can use. And then there is a very clever system inside the power unit itself where it recovers energy from the braking system. So every time the car brakes, it generates energy through an electric motor essentially, which then puts energy back into the battery. We have on these engines also another very clever piece of technology, which, because these are turbocharged power units, we can use the energy from the excess energy from the turbo, from the exhaust gases, to also put electrical energy back into the battery as well. So those sources of energy are all things that we can use to improve the efficiency of the engine.
When you think about how an electric motor works, it's at its best when it's not moving at all. And a petrol engine is at its best when it's got quite a bit of speed already. So I suppose the combination of the two of those, you're sort of filling in for the shortcomings of the other.
You're absolutely right. And it's one of the things that we're able to play games with as we go around the circuit. So, for example, when you first get on the accelerator coming out of a corner, we bias the power output much more to the electrical power delivery. And then as the car gets faster, that tails off and it becomes far more about the internal combustion engine, how you use that power delivery, and then also how you recover the energy at the end of the straight is a thing that we spend a huge amount of time trying to balance correctly.
We're increasingly in our conversation talking about strategic aspects of this. Obviously, a lot of this is going to come down to the driver. Does the car, though, learn the track? Or does the team behind the car learn the track as the car's going round, take some of that data and then tweak some of those things you've been talking about on the fly so that you can optimise performance even during a race as the race progresses?
So we've been limited in recent years in terms of how much we can actually allow the car to learn, which we would like to do because, frankly, computers inside cars would probably do a lot better job than even us humans. But we can certainly preempt some of the things that we might want to do. So the driver, particularly if we have a look at the steering wheel, you can see that there's a lot of knobs and buttons which seem a bit sort of superfluous for just steering the car left and right. But
it actually looks like a sort of game controller on steroids that you would have on your Xbox or something, but with a lot more buttons.
It does, and they're all brightly coloured as well, which really adds to the effect, I think. But some of these dials are also to do settings on the car that he can adjust as he goes around. Now, we predetermine what those are, but it really is something that allows him to adjust the behaviour of the car. So things like the rear differential, which is a part of the rear power delivery to the rear wheels, that can be adjusted as he goes around, or the way the brakes work on the front axle, the rear axle. All of that can be adjusted by the driver in order to allow him to, get the best behaviour that he can out of the car.
Are you also, because we've talked very much about how you're keeping tabs on what the machine is doing, are you keeping tabs on what the driver's doing physiologically? Are you monitoring the driver's heart rate, blood pressure, that kind of thing, reaction times? Are you collecting that sort of data to help them to learn and become better with each race?
We've sort of in the past left it up to the drivers to make sure that they're able to do what they need to do. And I think the ones who are performing the best are usually the ones that have prioritised that in their training and so on. We have sort of in recent years started to pay a bit more attention to how the drivers are doing as they're going around. It's a bit less important in Formula One than it is in some other things. There are racing series like Le Mans 24-hour races where drivers may have to drive at a sort of 3 hours at a time, and that's far more important. So they spend a bit more time worrying about how the driver is performing physiologically.
I'm not going to watch Formula One the same way ever again.
Well, hopefully you can see that there's maybe a lot more to it than meets the eye. But it's certainly, I think, a fascinating sport from the technology side of things as well as just the racing itself.
And when you became an engineer, did you see yourself standing here? And I mean, not talking to me today, but did you see yourself doing this as a job? Is this something you grew up thinking, this is what I want to do?
For me, this was always a sort of collision of really loving cars and also being very interested in aerodynamics. I was originally much more interested in aircraft, but as soon as I realised that you could combine those two interests together, it was really all I ever wanted to do. The thing about working for Formula One is it's incredibly high-paced and at times a very high-stress job, but it's never ever boring, and that's a good thing for me.
Dan, I can't thank you enough. It's been a pleasure.
Likewise, it's been a pleasure speaking to you.
British Formula One engineer Dan Fallows. Thanks, Dan. It was a really spectacular opportunity to go around the facility. I really enjoyed it. You can probably tell. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education, and it's supported by Rolls-Royce. I'm Chris Smith, and from everyone here at The Naked Scientist, thank you again for listening, and do tune in next time. Until then, goodbye.